Okay, let's talk about this FRQ here. We've got the box pressed against the spring. It's compressed, which means that it has some spring potential energy or elastic potential energy. The box then is released, and the spring launches the box horizontally along a track. So it's like this. When it's like that, it just has kinetic energy. And then it has enough speed to leave the ramp. So if you see here, this would have some UG plus K, which is how the type of energy it would have right until just about when it hits the ground. Then it's pretty much totally kinetic energy, right? Like right above the ground. Okay. So we're assuming there's negligible friction, so no friction, no force of friction, and the track and air resistance is also negligible, so no F drag. Super. So basically what they're telling us is there aren't any non-conservative forces. Nothing is taking energy away from the system. Okay, so eventually then it says the scenario is repeated using a different box with a greater mass. The spring is compressed the same distance. So they want to know, how does the max height in the second scenario compare to the max height in the first scenario? And we have to explain why without mathematically deriving a relation for H. So the total energy in the system starts with this spring potential energy, which does not depend on mass. So we're going to have the same total energy no matter what mass you put on that spring, which is then immediately converting into kinetic energy. The higher, so the kinetic energy will be the same, but if the mass is higher, the speed will be lower to compensate for that. So if M increases, V will decrease. Because I'll say E total doesn't change. Okay, so the E total doesn't change. And then if your speed is lower, then your max height is also going to be lower. So if, oops, not H. If V is lower, H is also lower. Right, because our height depends on our speed. The slower that thing is going while it approaches. Like if we slowly roll a ball up a ramp, even if it gets all the way to the top of the ramp, it probably just like falls off, versus if we whip it up the ramp, it goes really fast. It goes higher in the air. Okay. Students derive an equation for H, which they got sine of 2 theta kx squared over 2mg, which may or may not be correct, but is this equation consistent with my claim? It sure is. Yes, because I said height would decrease. If M increases in the denominator, H will decrease. Fantastic. Okay, so now let's take a look at student one. We're going to talk about the work done on the system only of the box. Okay, so that's kinetic energy only. If it was box earth or box spring, we could include some potential energy, but we cannot. So the student one says, at first the mechanical energy of the system increases because the spring does positive work on the system. True. So that's going to go under the correct part. That box or that spring sure does add energy into the system, so the mechanical energy increases because the spring makes that box move. So it increases its speed from 0 to more than 0. Then the mechanical energy of the system increases again as the box travels up the ramp because the box's potential energy increases. False. That is not correct. The only mechanical energy for the box system, which is just the box, would be kinetic energy. And we know as it goes up the ramp, the kinetic energy decreases, the speed decreases. Okay, student 2, the mechanical energy of the system remain constant while the spring pushes the box because the work done on the box by the spring cancels the work done by the spring on the box. That's false. The the mechanical energy increases because, again, the mechanical energy of the box system is just kinetic energy, and the spring has moved it from a speed of 0 to a speed of greater than 0. So the mechanical energy is actually increasing. Then when the block is on the ramp, the mechanical energy of the system decreases because the block slows down. Box slows down. Yeah, that's correct. So that's going in the correct bin. Next, does the mechanical energy of the box spring Earth? So kinetic energy, spring potential energy, gravitational potential energy. Does the mechanical energy of the box spring Earth system increase, decrease, or remain the same from the moment the spring is released until just before the box hits the ground? Justify our answer. It remains the same because this is energy is conserved, right? No friction, air resistance, nothing taking energy away. If air resistance was not negligible, how would that affect my answer? Well, then the mechanical energy would decrease because air resistance would remove energy. Okay, last part. The graph here shows the vertical component of the velocity. Vertical velocity is a function of time. It represents the time from the boxes in the air, from when the box was launched. So the box is launched. So right here, I'll put box launched, end of ramp. Right? And then here is going to be when it hits the ground. Okay. So this is from when it's launched from the ramp at an angle theta to the horizontal. How would the total area under the curve be different, if at all, if the ramp angle theta were increased, but still less than 90 degrees without changing the height at the end of the ramp? Okay. You might read that and be like, what? And like, spoiler alert, you might have done this entire FRQ. You might have seen, when you did this FRQ, you might have seen that theta at the beginning and heard them start talking about theta and been like, I don't know, trig, but really you don't even need to know that, any of that. Let's just think real quick. They want to know about area. We know that area of a velocity time gives us position. Okay, here's the key, my friends. This is the vertical velocity. So this is going to give us vertical position, aka height. It gives us change in, by the way, change in vertical position, aka change in height. So the area here gives us the change in height, which makes sense because the box is launched at a higher height than it is when it hits the ground, right? Let's go back. They're talking about from here to here. So yeah, that change in height better be negative. All right. On the slide I just got away from, it said that theta increased, right? So it's something like this, but that the height at the end of the ramp stayed the same. So if we're looking at change in height, even though now the theta has increased, the change in height of this box is still going to be whatever that height is to this height down here. That's all they're asking about. Okay, so because they say, I'm going back to the slide, because of this part right here, without changing the height of the end of the ramp, because of that, we know that area will be the same. Crazy, right, you guys? But true. Okay, have a good one.